in this prototype, we're going to write a prototype of the runtime of a game of Connect 4 that transforms user input into a point-in-time snapshot of a particular board. And so here's what we have. We have the board. We know it's 7 by 6, and we have what the plays are, what each player tried to do. And in the game of Connect 4, instead of saying put a symbol at a particular location, you say put it at a particular size and it falls down. There's this element of gravity. And you also need to be able to tell somebody, I'm sorry, this row is full up. It's not possible to put a symbol there. It's not possible to put a coin or a disc there because there's no place there. And so here, really, this prototype has more or less given me what I need to, in its requirements, what I need to do. Namely, I need to figure out how to model this idea of playing the game. Here you can see I have hard-coded the actual user actions because anything that increases my iteration time is going to significantly increase the total time to writing this code. And this is not a linear relationship. So for example, if I had said, oh, you know what would be really nice if I can just kind of play with this and I use like input to figure out what the input is, and then when I want to run this, I run this, dynamically. That might increase my checking time to 2 seconds, but it'll increase my iteration time to 4 seconds, 16 seconds, a minute. What I find is your iteration time has this nonlinear relationship with the actual amount of time it takes to make a change and to see where that change happens. And so this is why there's a strong preference to hard-coding inputs, because what I want is I want the fastest possible iteration time, because even a 1 second increase in time between make a change and see it happen might be a 15 second, 20 second, 30 second change between, okay, go from one working state to the next working state to the next working state. And this tends to explode where if you have a bad iteration time, you haven't locked down things with enough hard-coded data, you may find yourself doing a task that really only takes 5 minutes, but it took you the entirety of the evening. It's happened to me way too many times to risk it here. So what I'm going to do is I'm going to assume that I have this in the form that I want it in, and I'm going to assume that I even have the plays in the form that I want it in, although in this case, that's not a very hard transformation. This would just be plays.split. And here I need to convert those to the columns. So that's pretty easy. So this is just the column index versus the letter. So this is the column name to the column index for the column index and the column name. And we'll enumerate ASCII lowercase, and we're looking at the first 7 columns. Being able to generate dummy data and being able to do simple data transformations like this is one key to fast iteration. Being able to make use of random number generators to create relatively realistic data is one of these keys here. And it's a practice skill, and it's a practice skill for live coding, and it's something that's going to be valuable here. So here, why don't we do the following? We'll take our columns with our x for x in this, and this is really what we want to start with, this information, because this ties very closely to our underlying data. So our board is going to look like this. It's going to be a 6 by 7 or 7 by 6, depending on how you look at this, board with a fill value of, say, a null byte and a D type of single character Unicode digits. And we're going to print out the play, and we're going to print out the board. So here's each play, and that's what the state of the board is going to be. We know what we want to do for each of these cases. We want to get the corresponding column. So we'll get that play, and we'll get every row for that. So this is the corresponding column. Let's check to see if that gives us what we want. And we need to figure out where the symbol lands. Well, that's actually not too tricky, because as a consequence of our modeling, we should be able to do non-zero on the column to figure out all the spots where this thing is non-zero. And I guess that's not going to work directly on the data, but we can say if this is equal to that null byte. So it gives us every position where this is non-zero. And because we're looking at this top-down, we just need the very first one here. So that's actually where it lands. So the modeling of something like gravity is pretty easy here. Let's actually double-check that that works. Here's another trick that you'll see us do often. I didn't need to be running this full for loop and getting all that messy output. I only need to run one one pass of this, and I can just kind of hard code or hack up what the board should look like. So let's put a couple of symbols at some positions. Let's put some symbols at position, this is the row number, 5 and 0. Okay, and you can see that here that's our play, and that's our non-zero, so that's our board. And let's check one thing really quickly. Yeah, so this here should be, we've got to index this twice. So that's the position that it sees being non-zero. So here, is that correct? Oh, because they were playing in that first column. So you know what? Hard code. Okay, so is that correct? That doesn't appear to be correct. So let's rewind and let's see what's happening. Those are all the positions that it says are non-zero for this particular column. Let's look at what the column looks like to make sure we're grabbing that correctly. That's the column. Very good. And here we did this backwards. We're going to have to flip this thing. So let's, or we can just reverse it. Okay, very good. And that gives us the reversed coordinate. So the other trick we can do is we can grab the last one of these. The last one, that's a little bit better. So here, okay, so it says the fourth position. So let's actually put this at that position that it found and see if that works. And then we'll check this a couple more times. And I think we're actually on track. So this is the position, or this is the corresponding row that it's going to be in for the column, and we'll make that an X. So, and then we'll print out the board. And we'll double check that's the row and the position. This here is, and let's see what that broke. That's our board. That's our row. Let's see what the row and the position it wants to put this in. The row and the column. So it wants to put this at 0, 4. That's, why is that not correct? That is row 0. Oh, sorry, this is the, let's see, we have our column. Oh, actually here, this column, that's the whole column itself. So this should be the player's move. So it wants to put it at, okay, very good. So here, it wants to put it at 4, 0. Okay, so, you know, sometimes it gets pretty confusing if we're going quickly, but there we go. Okay, so it looks like gravity works. Let's fill that up. Yep. If we put like an O here, yep, it looks like gravity worked exactly the way we want. So this is pretty much the extent of it. This is our way of doing this. And so here, if we take that board and we run through these steps, we print the board at the end, we'll see what the board should look like based on that. And we can eyeball this and spot check it. Here, we know that this is actually each individual the different player moves. So this is a case where, you know, this itertools module comes up so much when we do this kind of rapid prototyping. Here, what we're going to do is we're going to cycle through the different players that we have. So we have players X and O, and we're going to cycle through those, through these players, and we're going to take that and we're going to zip it with the actual plays. And we'll move some of these things kind of further away. One of the things you can see when we move these pieces around is we're already setting ourselves up for, and this is, by the way, this is the column that they selected, and this is the player who selected that column. So this is the player symbol, and this here should be like that, and that should be like that. And here we'll put this all in line so we don't have that two of those column variables. There we go. So there we go. We've managed to model that. I believe this is all that we're required to do in order to meet this prototype. We want to make sure that we can assess a winning condition. So here, this is our simulator for the game, taking the initial state of the board, or however we want to call this thing, and here we can just yield this each time. Now, as we said, you know, moving from mutable to immutable is a little bit tricky. In this case, this is going to be somewhat inefficient because the easiest way for us to retain each individual step of this is to make a copy. A very big question arises. Do we make the copy inside this generator or outside this generator? Here, this is each individual state of the simulation. given the initial state, or which we called here the board. So this would be like the initial state. And here, what we'll see is if we're printing it out, it looks good because you can see each piece kind of making it onto the screen in a correct way. But if we're actually going to do some analysis, well, because this has been mutated each time, we're into trouble. So do we want this to be the copy here or a copy here? My gut feeling is, it's a very hard question to answer. My gut feeling would be we make a copy here because the choice of whether we want to allocate memory is something that we should put in the hands of the user. It's not something that we should presume. And this is where it's going to be a little bit tricky because we have to really carefully document, the board is assumed to be mutable, make explicit copies as needed. But otherwise, I think we actually have something that works to simulate the game. And all we have to do here in our loop is just check, if the game has been won using our criteria for the winning state of the game. And if so, we break out of this loop. And that's just code that we know we can write because we've written it before in a previous prototype.